At a modern automated container terminal, time is measured in hundreds of thousands of dollars per hour. An ultra-large container vessel carrying 20,000 containers is tied to the berth. Automated ship-to-shore cranes move massive steel spreaders at speeds over 4 meters per second. Automated guided vehicles cross the dock in a synchronized logistics dance. Then, everything stops. A commercial drone appears near the quay wall. The terminal's physical security team panics and switches on a newly installed high-power counter-drone jammer. The drone drops out of the sky, but seconds later, every automated crane on the berth shuts down. The high-power radio frequency blast instantly saturated the centimeter-level RTK navigation signals guiding the port's automated fleet. The ship misses its departure window. Demurrage penalties hit $250,000 a day, and the terminal operating system falls into total logistics chaos. Welcome back to BlackBox UAV. If your facility requires direct engineering analysis for port airspace security, contact our team directly at BlackBox UAV at proton.me. Today, we are analyzing why commercial counter-drone radars fail in container ports, the physics of multipath reflections from steel stacks, and how to design an IACS UR E26 compliant port defense architecture. Why do standard counter-UAS radars completely collapse inside a busy container terminal? The answer lies in radar cross-section physics and electromagnetic multipath propagation. Security integrators often treat a port like a flat, open field. But a container terminal is a canyon of dense, movable steel structures. A standard 40-foot steel shipping container acts as a massive radar reflector, exhibiting a radar cross-section between 1,000 and 5,000 square meters. Now compare that to a small commercial drone, which presents a radar cross-section of just 0.01 square meters. When a multi-gigahertz radar sweeps across a container yard stacked 6 containers high, the electromagnetic waves strike thousands of metallic corners and flat steel walls. The radar signals bounce repeatedly between the container blocks, a phenomenon known as multipath reflection. The radar receiver is flooded with thousands of false echo signals. The target tracking software experiences buffer overflow, creating dozens of ghost targets right inside the container stacks. The system either triggers hundreds of false alarms every hour or blinds itself entirely by raising detection thresholds, allowing a real drone to fly undetected directly under the crane booms. Even if a counter-drone sensor manages to detect a target, port operators face a second, even larger hurdle: maritime cyber resilience regulations. The International Association of Classification Societies enforces mandatory unified requirements, known as IACS UR E26 and UR E27. These standards govern the cyber resilience of operational technology networks connecting ships, port interfaces, and automated equipment. Most off-the-shelf counter-UAS command servers rely on unencrypted, legacy communication protocols to stream video and track data to security rooms. If an integrator attempts to plug an uncertified counter-drone system directly into the port's terminal operating system or industrial automation network, it creates a severe cyber vulnerability. A compromise on a single security camera feed can open a backdoor entrance into the entire port logistics core. During annual audits by classification societies like DNV, Lloyd's Register, or Bureau Veritas, non-compliant sensor integrations result in immediate compliance failures, threatening the port's operational license and invalidating maritime insurance coverage. The third critical flaw is the physics of automated crane navigation. Modern automated ship-to-shore cranes and automated stacking cranes do not rely on human drivers watching from a cab. They rely on real-time kinematic GNSS positioning paired with optical laser scanners to achieve location accuracy down to 1 single centimeter. The crane spreader lowers at high speed, locking onto container corner castings with microscopic precision. When security teams deploy standard wideband RF jammers to neutralize a drone, those jamming signals bleed across the L1, L2, and L5 satellite navigation frequencies. Even a low-power jammer completely blocks the differential phase-lock signals required for RTK operation. Deprived of centimeter-accurate coordinates, the crane's onboard safety computer detects a fatal navigation drift. To prevent a catastrophic collision between a 20-ton spreader and a vessel deck, the crane executes an immediate hardwired emergency stop. A single pulse from an uncoordinated security jammer freezes every automated crane along the quay, stranding berth operations and incurring massive vessel demurrage penalties. How do world-class automated terminals defend their airspace without freezing port operations or violating maritime regulations? by deploying an IACS-compliant, zero-interference defense architecture. First, engineering teams elevate high-frequency Ku and Ka-band microdoppler radars high above the container stacks on light towers. By angling the radar beams upward, the system completely avoids multipath reflections from steel containers while detecting drones above the crane line. Second, replace active RF jamming with targeted, passive detection networks. By utilizing high-precision acoustic microarrays along the quay wall and explosion-proof thermal imaging cameras, the system tracks targets silently with zero radio frequency emission.